Hello friends, welcome to lecture number 5 of Electricity and Magnetism, and today we're going to discuss about another Gauss application of Gauss law, that is electric field intensity due to a uniformly charged long solid cylinder. Remember, solid cylinder. Okay, so if you want to watch the previous lectures, then links are given in the description box. Okay, and before we start, please subscribe the channel if you are new to my channel, and also share with your friends and hit the like button. Also hit the bell icon so that you get notified when new video will be uploaded. Right, so now let's start. So electric field due to a uniformly charged long cylinder which is solid. Okay, so suppose this is a long solid cylinder. This is a long solid cylinder of radius capital R. So capital R is the radius of this cylinder, and it is positively charged, and the charge is uniformly distributed. Okay, so charge is uniformly distributed, and here we're gonna calculate electric field at a point P, at this point P. Here you can see, and which is at a distance of R from the axis of this cylinder. From the axis of this cylinder, it is at a distance of small r. Right, so in order to find the electric field using Gauss law, let us imagine a Gaussian surface. Let me imagine a Gaussian surface through this point P. Right, so let it be a cylindrical Gaussian surface. So this is a Gaussian surface of radius is smaller, right? So of radius is smaller. So first case we are considering in the first case that P is outside the solid cylinder. Okay, so we are going to calculate the electric field if P is inside this cylinder or outside this, as well as outside the cylinder. Okay, so first we are going to find the electric field at P when P is outside the cylinder. That means capital R is greater than small r. In that case we are going to do first. So here you see, let me assume that height of this Gaussian surface is suppose small h. Let me assume that way. Right, so now you see, and let me consider that charge density of this cylinder is suppose rho, volume charge density. Let me consider rho, and capital R is the radius of this cylinder. Let me write it properly. So its radius is capital R. This radius is capital R. Right, so let me write mention here what are the things we have considered, assumed here. So these are the things. Right, so here you can see, so here just wait, let me set it properly. Okay, just wait. Okay, now it's okay. Right, so here you see, so we have to calculate electric field at point P due to a long solid cylinder. Rho is the volume charge density we have considered, and capital R is the radius of the cylinder, small r is the distance between the point P and the axis of the cylinder, h is the height of the Gaussian surface assumed through P. Right, we have considered that way. Now let me take another slide. Just wait. Here you see, let me tell you one more thing. If rho is the volume charge density, so just let me get a new slide first. Here you see, for case 1, that means small r greater than capital R. That means P is outside the cylinder. Right, let me take that case first. So here you see, so we have that rho is the volume charge density. Right, that means charge by volume. Right, so here you see, that's why if you want to find the charge enclosed by this Gaussian surface, right, what will be the charge? So first we are going to take the, so here you see, if rho is charged by volume, then charge will be equal to what? Charge will be equal to rho into volume, right? Rho into volume, right? So therefore charge enclosed by the Gaussian surface will be equal to will be surface, let it be q. Suppose q is equal to rho into, we have to take the, you see, if you see the figure carefully, the volume of charge enclosed by this surface will be the charge enclosed by this volume, also this portion, right? Because the charge is present in this portion only, right? So hope you have understood this. So that's why we have to take the volume of this part of the cylinder, which is equal in height with its height is equal to the height of this Gaussian surface, right? So that is why its volume will be given by pi. Its radius is capital R, right? Its radius is capital R square into h, right? So that is why charge enclosed by this Gaussian surface is given by this. So let me take this one as equation number 1. Suppose let it be equation number 1. Now by Gauss theorem, we know that electric flux is given by charge enclosed by the surface divided by epsilon naught. This is by Gauss law. Now you see, let me take here 3 surfaces. First one is top surface of the Gaussian surface, and next one is curved surface, then third one is the bottom surface of the Gaussian surface, right? So let me consider that way. So now you see, in these 3 cases, the area vector which is normal to this surface, this makes 90 degree with the electric field. The direction of the electric field is always outward from the positive charge, so that should be in this direction, right? And this is the area vector, right? Similarly at this point P, here you see, if you consider a surface element ds, so ds vector will be in this direction, and also electric field is also in this direction. So here in this case, angle between these 2 vectors will be 0 because they are parallel. And for the third case, for this surface, so here is the direction of the area vector, and again this is the direction of the electric field, right? That is why the angle between these 2 vectors is 90, right? So now you see, we can write these things, we can split into these 3 terms, right? For the first surface, E dot ds will be EDS cos 90 degree, right? Then for the second surface, EDS cos 0 degree. Then for the third surface, EDS cos 90 degree, again is equal to q by epsilon naught, right? Now you see, cos 90 is 0, that's why EDS cos 90, this third surface and first surface, through these 2 surfaces electric flux will be 0, right? Now we got only this term, cos 0 is 1, this will be equal to 1, so 1 into EDS is EDS. So let me go to the next slide. Let me copy this step first. So here you see, The second surface is the nothing but the curved surface of this Gaussian surface, and its curved surface will be 2 pi small r into h, right? Hope you know the curved surface, how to find the curved surface of a cylinder, right? So that's why E integration ds we can write 2 pi r square, sorry, not r square, r into h q by epsilon naught. Let me draw the diagram here also. So here is the diagram I have drawn again. So now you see, we have already got the value of q that we have got from equation number q is equal to rho into pi capital R square into h. We have got that. Let me show you. So here you see, in equation number 1 we have got q is equal to rho into pi capital R square into h. So let us use this equation number 1. Let me copy these things. So this is the equation number 1, right? This is the equation number 1. So let me use this equation here. Okay, so then what you will get? Then you will get E 2 pi small r square into h. Instead of q you can write rho into pi capital R square into h, right? Capital R square into h by epsilon naught. So now let me clean these things. So here, so we have got this result from equation number 1, right? So now you see, that's gonna be equal to, here you can see this h cancels, pi gone, right? So it can implies E is equal to rho capital R square by 2 small r epsilon naught. So we have got this. So this is what? This is electric field at a point due to a long uniformly charged cylinders, right, at a point P. So P is outside the cylinder, right? So electric field at a point P due to a long uniformly charged cylinder outside the cylinder. Right, that means for the case of r greater than a small r greater than capital R, right? Now what if this point P lies on the surface of this long cylinder, right? Then small r will be equal to capital R. So let me go to the next slide for the next case. So let me copy this result. So here you see, so if small r is equal to capital R, that means if P lies on the surface of the long cylinder, right, then what we will get? Electric field E will be equal to rho capital R square by 2 capital R into epsilon naught, because small r is equal to capital R, so it is replaced by capital R. Then this capital R cancels this R, capital R square, so it becomes E is equal to rho R by 2 epsilon naught. This is what? This is electric field due to a long uniformly charged cylinder, solid cylinder, at a point on its surface, right? So we can assume that way. Now you see, we will get another case, that is what, if r is less than small r is less than capital R, then what we will get. Let me go to the next slide. Now you see, if small r is less than capital R, then this diagram will be changed, right? Let me clean this. So here you see, the point P lie inside the solid cylindrical conductor, right? So suppose this point is P here. Now this point is P, okay? It is lying inside the cylinder, solid cylinder. This is suppose P, right? This point is P. So here it is at a distance of small r, right? So let me draw it properly. So here is the cylinder, long cylinder with radius small capital R, and we have taken a point P which is at a distance of small r from the axis of this, from this axis of the cylinder. So here you see, then again if you assume the Gaussian surface, cylindrical Gaussian surface this way, let me draw it, of height small h, of height small h, then what will be the charge density? So that means if P lies inside the cylinder, right, then here you see Q, surge enclosed by this Gaussian surface, will be now rho into, now we have to take this small radius, we have to take this cylinder only, because P is not outside the or on the surface of the this solid cylinder, it is inside the solid cylinder at a distance of small r from this. So we are going to take this portion only, so that's why rho into pi small r square into h, small r square into h. So now you see, if you go to previous slide, here you see if you let me go to the previous slide. Here you see, if you go back to this equation in this case, so this, let us suppose this is suppose equation number 2, okay? So let me copy this equation. So from equation number 2 we have got this, right? So now in this case you can see that if you replace this Q by this value, then what you will get? Then you will get your rho pi r square into h by epsilon naught. Here again this h cancels, r cancels, r square to get r only, pi gone, so we're gonna get only E is equal to rho small r by 2 epsilon naught. That's what we will get, right? This is what electric field. Electric field due to a uniformly charged long solid cylinder at a point at a point P inside the cylinder. So this is all about electric field intensity by a long uniformly charged solid cylinder. So hope you have understood this all these three cases. So if you like the video, if you think this video is helpful, then share with your friends, hit the thumbs up button. If you are new to my channel, subscribe the channel.